A good day to the both panels. I are Dr. Muzaffar and Ahmad Sayuti. Today, I will be presenting the title of the project, Design and Development of Bowtie Rectangle for Energy Harvesting. My name is Yogasheni Murti. I am from 3BET S1/2 under Supervisor Nurul Halim bin Hasim and Co-Supervisor Dr. Muhammad Inam Abbasi. Would like to present the BDP1 Bachelor Degree Project 1 presentation. Introduction. In general, almost all electronic devices are powered by batteries. What are the common issues faced by the electronic devices? Increased in device size and weight. Regular maintenance are needed for the battery. Is either tough or expensive due to the inaccessible environments. What is the solution? Bowtie rectangle for energy harvesting, as energy harvesting can supply power. Problem statement is the basis of a research. A bowtie antenna has a poor transmission efficiency as it operates during at the lower frequency range. A true biconical antenna can stick it up to 360-degree pattern and in both directions. But unlike bowtie antenna, it's a two-dimensional version, which causes RF signal limitation. Objectives and scope. Objectives and scope are the main of the project. Design and simulate a bowtie rectangle with a frequency range from 500 MHz to 3 GHz for energy harvesting. Bowtie rectangle is to work in a 360-degree pattern and both directions. Fabricate the bowtie rectangle on PCB. Let's look at the scope. Rectangle should work between the bandwidth of 500 MHz to 3 GHz. Type of antenna is microstrip slot bowtie antenna. And final one, bowtie antenna will be designed in CST Studio 2019 and rectified in ADS 2019 softwares. Methodology. Before that, I would like to say that methodology is actually the synthesized gathered data that has been done in literature review. The softwares that are used in this project, CST Studio Suite and also ADS, Advanced Design System. Next is the flowchart of antenna design. First, background study and literature review on bowtie rectangle for energy harvesting, as in chapter 2 of the final report, literature review. Next, design a basic antenna in CST and matching network and rectifier in ADS to familiarize. Next, design the rectangle according to the parameters which will be calculated. Then, simulate the design and analyze the output. If it achieves the objective, the design rectangle will be fabricated. If not, we have to redesign again rectangle according to the calculation. What is the parameter list? This is actually the parameter list that have a window in CST software. These are actually for the substrate, ground plane, dielectric, insert. These are the parameters. Next, rectifier design flowchart. A rectifier receives the source from antenna and then it transfers to impedance network. Impedance network is also known as matching network or impedance matching, is the same. And then it goes to lump elements, inductor or capacitor. And then it converts from AC to DC. If it achieves, the rectifier circuit will be executed. If not, we have to go back to the convert from AC to DC. What are the material and function and item and quantity used in the ADS for the rectifier? There are 4. Diode, convert AC to pulsating DC. Resistor, determine the energy delivered to the load. Lump elements, concentrate the power transfer at specified frequencies. PCB provide mechanically support and a pathway to its electronic components. The quantity for resistor, lump elements and PCB are 1 except for diode 4. Energy harvesting flowchart. It's the same as rectifier design flowchart. The difference is after it achieves, it goes to the load. And if there's a problem, we have to check back on the lump elements. Matching network. What are the types of impedance network? There are 4. Series L component, shunt L component, pi network and T network. The series L component and shunt L component, you can see is the differ of the arrangement of capacitor and also inductor. It's the same as types of L network configuration. There are 8 types, where some of it are C series, if not C parallel, L parallel, if not the C series. But the Z in and ZL remains the same. Let's look at the initial result. First is the antenna design. Front view, perspective view, back view. These are the view from the CST software of microstrip slot bow tie antenna design. Next, rectifier circuit. As we know, this is in ADS. As how I mentioned earlier, 4 diodes, lump element and also resistor. Bridge topology circuit, this is the simulation of energy harvesting with the rectifier. And that is P1, which is power transfer, which is to replicate the antenna, as in ADS there is no component for antenna. Conclusion. There are 3 primary goals for this project. First, the bow tie rectangle must work from frequency of 500 MHz to 3 GHz. The bow tie rectangle must be able to stick it up to 360-degree pattern and works in both direction. Finally, able to fabricate the rectangle on PCB. Let's look at the Gantt chart of BDP1, which is for the current semester. Project title selection, which will be done by supervisor and registered by the supervisor. And then the research goes on until the ending. And research is very important for literature review. And then to prepare the logbook, proposal preparation, progress work, and finally ends up to the presentation. And I've also added the Gantt chart BDP2, which is the progress for next semester. It's the same as BDP1, but this BDP, which is for next semester, focuses more on chapter 4 and 5, as this semester focuses more on chapter 1 till chapter 3. And the same thing, it goes on and ends up with BDP2 presentation. Demonstration. These demonstrations are only the preliminary result. These are not the actual result, and there will be more work needed to be done. Let's look at this slot bow tie microstrip antenna. As you can see, S parameter is also known as return loss as 1, and a good antenna will always be at negative 10 dB, if not less than that. And as you can see in the figure here, negative 10 dB is 2.375 GHz, but more work will be done on this. Next, voltage standing wave ratio, VSWR. A good antenna would be between 1 to 2. The figure chooses at 2.357 GHz. But there are more work to be done due to we need the VSWR to be at lower frequencies. Radiation efficiency. This, as you can see, from negative 99 dB, it reduces up to 0. Okay, and frequency 1.75 GHz. This could be happen because of dielectric loss or even the antenna itself. Next, the result of bridge rectifier. Reflection coefficient is actually regarding the resistor. Okay, it resonates at 2 GHz with the input of 50 ohm. Power conversion efficiency of bridge rectifier circuit with different values of input power. At 10 dBm, as you can see, 17.36% is the most incredible efficiency. And it's begin to fall down as the input power. At negative 40 dBm, 0.0002% of minimal efficiency achieved. The suggested rectifier can produce DC voltage for low RF incident power. That's all from me. Thank you so much for listening.